So we are going to begin with the theory of integration, because no doubt all of us know integration. We all can integrate things using antiderivatives and so on. Okay, but we want to do theory of integration. We want to make precise what it means to integrate a function from a place to place, and when do we say that the integral is existing, and what are the techniques and maybe some theorems. Okay, theory of integration. Okay, yeah. Okay, so basically it starts with the goal, maybe crudely put, is to develop a mathematical theory using which we can find areas of sets. Okay, mathematical theory to, can just say, find or make sense of, rather. That's I think more important thing. Make sense of area of sets. To begin with, this is what it is, but it goes a long way after that. But okay, for now, for us, we will just keep the sets to be in R2. Okay, just a second. This is what it is. Okay, so then let me ask a question. If I take, and I have discussed this kind of things with maybe Rasu, who's here, would know a little bit. Let's see how Manas, I mean, all of you, both of you know this, but how you have done it, it depends. So let's see. If I take this arbitrary set S inside R2, okay, what should I ask? I should ask, I mean, if I say what is area of S, I'll just say what is A of S. Okay, this notation you can understand. Okay. And what does this question mean to you? Hi Chandan, we have just started. So how would you answer this question? What is area of S? Or maybe to put it more specifically, maybe I can remove it, find area. If someone asks you find area of S, then how would you go about it? What should be the procedure? Okay, so for those who joined just now, we just started. Just doing today, the goal is to start with theory of integration. I'll do the problem solving in the end. So I have done this for some of you, right? When we took subsets of R, we took some very strange subsets of R and we tried to find the area. How did we do it? Can you extend that thing to this situation? Because essentially the Riemann integration that we will do first is a special case of this, which this we won't do in full generality, but we want to just see the idea. The idea is very clear from here. Then we'll see it in Riemann integration when the set is from a function and such. Oh, today everybody's here. Okay, so I'll just say the last question here. I mean, just basically we just started. If I just take an arbitrary set in R2, then what does it mean to say find area of S? I mean, how would you go about it? Okay, All of you would have different versions of this. You would know different versions of this maybe, or maybe you don't know. Then just think. How would you go about finding area of S if just a set S is given to you? Again, repeating. So for some of you, I had taken some strange sets in R2. Some like we took Cantor set. We took the rational set of rationals in R, not R2. And there I had described a specific technique to make sense of first, not find, to make sense. Sorry. What does it mean to say finite? So I would say S is bounded. Okay. S is bounded. Finite is not such a good. S is bounded. So I'm not defining bounded, but you can understand what it means, more or less. So try to extrapolate what you did for R for those who have done it. Otherwise, just think in general. How would you go about it? Because in this setting, we can see the idea very clearly and loosely also. Then we can go to the case of function, and there we will do basic Riemann integration. So just say anything, like how would you go about finding the area of this? Remember the okay, unit squares. Okay, how many unit squares? So this is the idea of Chandan. I want others to maybe comment on this or improve this. How many unit squares in S? So why is this good and why is this not good? Why? And we all, yes, no, but it's a set in R2. No, it's a set in R2. Yeah, so we already have measure of distance. Yes. So why is unit squares not good enough? So it's not precise enough, right? Obviously, because our physical intuition tells us that this is not precise enough. So we don't take this as a definition. Do you guys agree? Yeah. So it's, yeah, because you can just see that there is only like this one unit square here, or maybe you can fit two, but then that's not a good measure. So unit squares is not precise enough. So we are basically trying to form a definition using our intuition. Okay. So then what do we do? How do we get a more precise area? Because we already have a sense of what area should be. So how do we get there? We have to use squares. You can use other things, but we can use squares as to start with. Simply you can use, yes. No, bounded just means that basically that there is a rectangle such that, you can place the thing inside it, so that S is inside that rectangle. See, closed is not such an easy thing to define, so I'm not saying it, but you can assume that, yeah, there is a boundary for it. Okay. Yes. So for area can still be defined. So we don't, okay, so for the moment, let's assume that S is closed. In the sense, let me give a loose definition of closed. but you don't have to assume this. We'll see. Now, what do I mean by closed here? I mean that S divides a plane into two parts, an inside part and an outside part, right? That's what I mean. The boundary of S divides a plane into two parts, two disjoint parts, basically. But you won't need this to define area. Okay. So basically, we can use. What is that? Oh, you want to take that? No, that's not such a good definition, because you see, you could take something like a diamond, right? Now you see, you have this point which has the coordinate x, but maybe whatever, like you understand that this point has a certain x coordinate, but no other point has that x coordinate. So that is not making too much sense to me. So let's not go. So it's not very important what S exactly is. You can just assume it's this loose thing. I'm interested in the idea of how to find the area, not the geometry of S and precise notions like that. Okay. Let's focus on trying to, get a mathematical way to get to what we feel is the right notion of area. Okay. So basically, to be more precise here, we want to be more precise, and so we can take smaller squares. And this is the kind of a, so how would you make this? How would you go from here? If I tell you that you should take smaller squares, I mean, as small as you want. Okay, so let's see. So you fix some epsilon greater than 0. Okay, and now you so the way to say this would be count. I'll just say this like this: count number of epsilon length. You understand what this means? Epsilon length squares strictly inside S. Is the statement precise enough? So I'm just going to take squares of length epsilon many, and obviously disjoint squares. Okay, let's count number of epsilon length squares. I mean disjoint squares. They should only intersect at the boundary, obviously. Otherwise, yeah. So basically, I'm just going to take a mesh, which has epsilon. Each cell is epsilon length. Okay, and I'm going to cover up my square with that epsilon, with the squares with this mesh, and I'm going to count the number of epsilon, number of squares of this epsilon length. And then I will say, let epsilon tend to 0. So maybe I will say here, I should just put a notation for this. Let's say that this is a epsilon of S. Okay. And then the limit, find the limit. I'll ask you guys to make sense of this. And I will take this as my area. Now try to make sense of this first. Then I'll try to explain this if needed. So I fixed epsilon, some epsilon to begin with, just fix it for a moment. And then I took a mesh in which the squares are of epsilon length. I covered S. Some squares are partially inside, outside. I don't want them. I want the squares which are strictly inside. Okay, this gives me a good approximation, right? But I want the best approximation. Is that right? That will give me the area. And so I'm taking smaller and smaller squares and then seeing how many of them are there. Well, actually, this is slightly incorrect. This should be, so number of squares times epsilon square, because that is the area. That is the approximation, right? Basically, this figure, the area of this figure, if you assume it's already defined, the area of this figure will kind of be bigger than number of squares of epsilon length times epsilon square, right? But we don't want to define area. So, but no, yeah, area of, so for a square, we are assuming that the area is square of the length of the side. That is an axiom, yeah, that we are assuming. I had mentioned this earlier in once, right? That there are some axioms that you start with the unit square, and if you take the ratio, then area goes to that ratio. You can translate a figure, area doesn't change. Those axioms are obviously there. I'm just assuming them. I mean, those are, yeah, little things. But do you see why this is a good definition? It's kind of tending towards the actual area. Would anyone like to summarize this construction? Why is this good? Or is there anything missing in this? The idea is to approximate from inside. Approximate in the figure from inside. Which are fully inside. Yes. So when we take smaller and smaller squares, then we are kind of more or less filling the set S, right? We are kind of filling the set S. So as you take smaller and smaller squares, your approximation gets better and better. Is that fine? And so it's kind of okay to say that this should be, this is a good definition of area, maybe. Any questions? Ask me some, because there are a lot of incomplete things I've said here. So, I mean, that is to precisely complete it completely, that is difficult, but still there are some obvious incomplete things I've said. So any questions? Manas, is this construction okay? Or if you have any questions? Okay, right. Okay. So first of all, you guys tell me, why should this limit exist? That no one asked. Like, what's the guarantee? Is there a guarantee? So I'm not asking for a proof that the limit of this exists, but why should we expect that this limit will exist? Q, no, that is epsilon. That is, yeah. So basically, that's the approximation up to with epsilon squares, epsilon size squares. Okay, so the reason why this should exist, though it actually doesn't always exist, the reason why this should exist, anyone can say. So basically this is a function of epsilon. As epsilon is going to 0, we are taking the limit. It doesn't always exist, but you will not be able to construct a counterexample. It's extremely non-constructive, in fact. But still, why should this exist? It's a very good reason. And the reason is, and this plays a major role in Riemann integration also, is that as the epsilon decreases, we've kind of already said it, as the epsilon decreases, the approximation gets better. So when epsilon 1 is less than epsilon 2, a epsilon 1 s is bigger than a epsilon 2 s. Yes, it must also be bound. No. It's so see, just because it is bounded, it doesn't mean that. Uh, yes. So no, actually, you are right. Actually, you are right. So what I was thinking was something, but that was wrong. Yeah, you're right. This should always exist. Okay. So let me make what Adish said precise. First of all, before that, sorry. Before that, do all of you see this? I'm not asking for a proof. Okay. So fine. This is okay. This is the reason. This is the reason why this exists. Now to make it precise, just to put the notation properly, I will just call this as f of s, sorry, f of epsilon. Okay, f of epsilon. Now you can just see, okay, f is an increasing function. Remember, I'm not asking if f is continuous. That is a different question. I'm not asking that. F is increasing. Wait, f is increasing and decreasing. F is decreasing. F is bounded. Why is it bounded? Because the region is bounded. Okay, so, and this, if you do not have not proved it, you can prove this. This is a simple fact. I'll assume it here. F of epsilon exists. F is decreasing, right? So that's why this limit actually exists. It should be the infimum. Yeah, no, you don't need the monotone convergence theorem because that is for sequences. But yeah, you can use that. You can use that, or you can just take the infimum and you can prove that that is actually the limit. It is simple. So I'm not going into that. You can try to prove that. Okay. So then even then, is this a good definition? So you can, so all of you would know, some theory definitely of Riemann integration, vaguely. You can match it with that also, or anything, and see, is this good enough definition, or sorry, or are we still missing something? The reason why we are doing this, because now after this, when we make this set, the graph of a function with those vertical lines and so on, then when we do the theory, the various definitions and notations will be all just completely natural, so that we can then focus on the function aspect of things. And so eventually the goal would be to be able to prove that certain strange functions for which an obvious antiderivative doesn't exist is integrable, or is it not integrable, to prove some theorems about when some strange functions are integrable. That is the goal. So, But obviously this idea is useful either ways. So a lot of problems can be given just from here. Okay, we're not doing anything. So what else is missing? Just think. Actually, I also need to think of a good way to say this. I don't know, actually, because I cannot give a counter example. It's extremely non-constructive. There is something, but just think, what else is missing? Okay, I think there is one way in which I can say this. What if f was not continuous? Would you be happy? So what do I mean by f is not continuous? Yes, yes. Can you, I think you've said something interesting I didn't understand. Can you say that again? Mm-hmm. Mm-hmm. So are you only rubbing off the boundary or you, what are you doing? The rubbing. Oh, just one point. No, no, no. Oh, okay, okay. No, no, no. But then, so if you just rub off a point, you see, then you can always take squares around it, right? Yes. Yeah, so that's a good point you have made, but let's see. So what Adish is saying is you take the set S. So assume that S is very straightforward because there could be all sorts of strange sets in R2, okay? But let's say there's a straightforward set S. And now if this yellow point is deleted, then does this affect the area according to our definition? Sorry, can you say that again? Yeah, point has no area because you can even go by this definition and prove that we don't have to define because smaller and smaller squares, right? So its area is less than any epsilon, so it's 0. Yes, it will not affect. And even we can even just I can say this directly from the construction because I don't have to even specifically construct things around it and so on. I can just make squares. Um, well, mm, yeah, because so Adish, do you see like if I let's say I consider that point in the set for a second and I make the construction, okay, then eventually I will have smaller and smaller squares. And each time I get a square around that, I'll basically not count that square. Okay. But then the contribution from that only one square is going to be epsilon, where that epsilon goes to 0. right? So it's not going to affect the area, because I mean, I'm going to take squares around it, means in the sense that I'm going to take squares which don't contain that point, right? But if I just take squares blindly because I'm going to put a mesh, I'm just not going to count this pink square. But this pink square is going to get smaller and smaller. And so eventually the square which I'm not counting has no contribution. So it's not going to affect that's not going to create a discontinuity, okay? Or create a problem. So what will really create a problem is hard to say, okay? I can vaguely say that there's something very strange can happen with the boundary and so on, but just hypothetically, if you assume yes, right. But then what does it even mean to say discontinuous? No, it won't jump because the limit will jump. Yeah, the limit will be suddenly will be different. So what I'm saying is that first you have to define what f is at 0, right? So you define f of 0 to be this limit itself. That's a natural way to define it, right? Now, after you make this definition, if f is discontinuous, and it's hard to imagine how this could happen, but let's say if this happens, okay? Then isn't this very bad if f is discontinuous? So I'm not asking how this could happen. I'm just saying that assume it assume that if this happens, then isn't this very bad? Like, so f of 0 is very different from where the values were tending. So f was decreasing, whatever, like at 0. So right. So the way how would I say this? 1 minute. No. So I'm just saying something wrong, right? 1 second. No, sorry. So if if you define f to be like this, then f is not discontinuous. Sorry. So what does it mean to say that f is discontinuous? That's fine. That's fine. No. So no. So it's what I said is wrong. In some sense, not wrong, but it's not a good way to say f is continuous, because if I define f of 0 to be like this, then yeah, then it cannot be discontinuous. So f has to be continuous. This implies f is continuous by definition, right? F is continuous. Like, this is just the definition of continuity. Oh, yes. No, so I mean at 0. I don't know about the other points. Yeah, I mean at 0. Yeah, obviously. Okay, at 0. Right. But this is not such a good definition, because even if you have seen in Riemann integration, we take like something called upper sum and lower sum, right? I mean, to really be foolproof of the fact that this area is not something bad, we would also like to take an upper approximation. Okay, so to be really sure, we have to also take an upper approximation. That's all I'll say. Yes, yeah, then only we can safely say that this is the area. Okay, but let's see. Okay, so I'll just write this to be, so like this just, I'm trying to say it in a way that this is a natural questions, and then we just trying to formalize it and make observations. And yeah, to be really sure, we take, and so this is my bad, because there are, I think, simple examples of this also, but I don't have them with me. I mean, because I was always of the impression that The examples would be very non-constructive, but let me say. So to be really sure, we take upper approximations also. Okay. What do I mean by this? So upper approximations is clear. We basically cover the set, right? We fix epsilon and we count the number of epsilon size squares um, which strictly contain S. But that's not complete. Can anybody make this upper approximation precise first? I think that's a good thing to think. Yes, that should be that, right? So we fix an epsilon greater than this, and I can count, just say a number of squares. So we put a mesh, and then we count the number of squares of, I just say, number of epsilon squares which intersect. So you see, they have to intersect with S. Otherwise, it doesn't make sense. So that's what we have to put in the definition. Okay. So it has to intersect with S. And then for this, so let me just call this A epsilon. A minus is just a notation, A minus, okay, for the inner approximation. And for the upper approximation, I will say A plus epsilon. And once again, we'll do this, right? Multiply it with epsilon square. Now, what should we now do next? So once again, we should take the limit, right? So now we take the limit, and let me call this A minus, upper one, that one, the inner approximation one, that's A minus, naturally. Once again, we take the limit, epsilon goes to 0. Epsilon is this A plus, this was minus. And this is this, okay? So why should this limit exist? Because this time it's an increasing function, right? As you take better and better approximations, your, 1 minute, hold on. Second. Oh, wait. Yeah. So as you take smaller and smaller epsilons, your area would actually decrease. Is that right? Because that's again very natural, right? So you have, let's say, this square, and you counting this area. But then if you're taking a better approximation, let's say next time you subdivide it like this, right? Now, okay, maybe this one will not really show the thing. Let's say you subdivide it further after some stage, okay? So maybe, yeah, like this. Now you see, you will not be taking this one, right? Because that's completely outside. So I mean, the parts that were a little bit outside will become completely outside, which you take smaller epsilon inside. So as you decrease the epsilon, your as you decrease the epsilon, the area is also decreasing because we're letting go of these things, extra things, right? So this is decreasing, and so this limit should exist. Okay. What's next? Now what? Right. The two limits, I mean, if the two limits are not same, then something is very wrong, right? So, sorry, we want the two limits to be same. That is the key. 1 minute. Okay. So we say that A of S exists if A plus is equal to A minus. Okay, and then we define this to be the area. Okay, but we need to do this check. Sometimes the upper Riemann sum may not be equal to the lower Riemann sum. Obviously, the upper one will always be bigger than the lower one, bigger than equal to, right? But they may in the end not be equal. Now, it's hard to imagine that, but there are some strange sets where the boundary actually ends up having a contribution. Okay, so, but those are extremely difficult to construct, at least, okay? Like so it's like you have an infinite perimeter, some very strange boundary. I can't obviously cannot draw it. So the boundary also ends up having a contribution. Okay, and so the upper and the lower have a difference. And in those figures is strange, and we don't want to say, we don't want to assign. Yes, right. Sierpinski's triangles. Yeah, so that's a fractal, but it's hard to prove. Maybe okay, no, that's not hard to prove. Yeah, so you do some iterations or something like that, right? Yes. Yeah, those things keep coming up, but right. It's hard to define a notion of dimension for those things also. So those things will have fractional dimension. Okay, but since dimension is not a quantity which we are interested in for sets right now, we're just interested in area. So we're just doing this. Yes, so fractional dimension. So basically, so dimension is the way dimension is usually defined. It is, we think that it's an integer. Okay, but for arbitrary sets, how should dimension be defined? So it really depends on the definition of dimension. Okay, so usually dimension will be defined as given a point, how many pieces of independent information you need to locate that point. Okay, maybe that kind of is one definition. But then there is a very abstract definition of dimension using using areas. Okay, that is a little complicated to say, so I'm not saying it. In fact, I don't even have to just see the definition myself. Okay, but with that definition of dimension, but first thing is dimension is trying to capture, what is it trying to capture? It's trying to capture how many pieces of information you need to locate a point. That is a dimension. Okay, then you may say, well, if you're in R2, then why is it not just 2 for every point? No, 2 is the maximum. But if you're in a special subset of R2, like if you're already told that you're in a special subset of R2, then you may not need 2 pieces of information, right? For example, if you're on the graph of a function and you're told that you're on the graph of the function f, then to locate points on this graph, you don't need 2 pieces of information. You just need the point 1 x coordinate. And so we say that the graph of a function is one dimensional. And you can agree with that also. Okay, so that is that is the most general principle on which different definitions of dimensions are based. But there are many definitions, and it's a big thing. Okay, and all this is a prerequisite. Okay. Yeah. You'll get 2 points, meaning okay, yes, but yeah, so that's actually a deep question, as I interpret it. So except for these 2 points, no, but even at this point, locally, you need only one piece of information. Yes, yeah. So then in that sense, you would need two pieces of information. Then you only need one. Yeah. So that's the thing. That's why dimension is non-trivial, because from one perspective, it may look like you need two definite two information, but then if you have a smarter way to say it, then there is only one information needed. So in that sense, it's only one information needed, right? So this is the dimension one. Yeah, because if you already mentioned that if one already mentions that the radius is one, which is fine, that's not a problem. No, there is no straightforward way. Okay, but yeah, there are many interesting ways, and that is basically the theory of manifolds. Something which is very strange, but then around a point it is very good, and then what is that good thing like? And so then that's the number of informations you need, and then you take the maximum over all points, and you get that. But it's gets very basically the point is that in the end, like I gave you this small example of this graph of a function being one dimension. This is the beginning. Basically, when we see some complicated figure, we try to see if it can be broken up into graphs of functions, and that is what is known as the implicit function theorem. Okay, but we will see that later maybe. Okay, yeah. So then in this way, one goes into the definitions of dimensions. There are other definitions suitable for different purposes. Basically, a set is a complicated thing. We want to understand it through a number. Now, that number could be area, that number could be dimension, that number could be different things, whatever is suitable. So, for some sets like Sierpinski's triangle is said and so on, it ends up being fractional. Now, it doesn't really make sense if you directly use the word number of parameters, but it turns out to be fractional once we generalize things. But yeah. Anyways, let's come. Um, So we basically want this upper sum to be equal to the lower sum. And sometimes it is not. So when it is not, then we say that the shape S doesn't have an area. Okay, then we say that the shape S doesn't have area. And that's it. Otherwise it has an area. This is the definition of area. For the two upper and lower ones will be different. Even in Riemann integration case, we will see there are some functions for which upper and lower are different. So we will see that in the examples and exercises. Okay. So now so we have talked about this, all this is good, but now let us try to see this in the case of functions and, make sense of them and then maybe prove some results. So any questions so far about this? We've got a general picture. The general picture will be helpful for you throughout when you're doing different kinds of integration or integration type problems if you're doing, which is not directly framed in terms of integration. Okay, whatever. Okay. Now we want to look at area under this is, you understand, but I'll define it also. Under this is called epigraph in terminology, but under graphs of functions. So this will be very familiar to most of you. You take this thing, this is a function, and epigraph just means that you take a domain, so you have this endpoints and basically this region. You can write it clearly, but you understand what this is. Now we want to make sense of area of this. But we can use squares, but we don't use squares in this case because it turns out that, so we basically just use rectangles. You guys know this, right? You take a partition of this, and you can tell me why you don't use squares. So we use these strips, and we first of right? And also it doesn't lend any new information, right? Because right, because if we use a square, but also the answer will not really be different. Okay, so let me first make precise what I mean by using these rectangles. Yeah, so let's put the context clearly so that I can also say clearly. So this, and I'm not assuming continuity. Continuity is a very special thing in area theory. Okay, continuity and integrability are different. I mean, obviously continuous functions are not obviously, but continuous functions are integrable. That's not obvious. We will see. And with that, using that, we can revisit our sequences, see sequences, how much we can use those theory, those in this case. But yeah, continuous functions are integrable, but there are many more functions which are also integrable. So we take this function f from a to b to r, and yeah, then what do? We take a partition, or maybe I can just say a fixed epsilon, just to keep it analogous. Fix an epsilon and take. So I'll just take a very special partition. Okay. Later on, I will show that it doesn't matter, but or you can show it, but take a special partition. This is good enough. Take a partition of AB. This is analogous to putting a mesh on the thing. Take a partition of squares, but in this case, we take a partition of AB as, no, you can understand, A plus epsilon to epsilon and dot 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 till you can understand this till it goes to B. It will at some point. We know that Archimedean property, if you want to say. We take this and then yes, the partition in general doesn't have to be regular, and sometimes irregular partitions can help you to prove things more easily. Like if there are some bad points, and you can take a partition which can, engulf that bad point always, or something like that. Okay. But the answer does not change. Like even if you just stick with these partitions and you take epsilon to be 0, you take the lower sum, then you take these partitions and take upper sums, means, which contain the function, like strictly the graph, contain the region strictly, and you take the limit of that. Then those upper and lower are equal or not equal. They can be completely determined by these partitions. Okay, these good partitions. One doesn't have to consider arbitrary partitions. These partitions are good enough, but those partitions are can be useful to bring out other things. So first of all, what do we really do? We take this partition and then for the rectangle, then for maybe for here to this, for this, we basically take the area of the corresponding rectangle, which is completely inside. Say we take the area of the corresponding rectangle. What do you mean by corresponding rectangle? You can understand. So let's say from here to here, I'm considering this piece. Then I want to take the area of the corresponding rectangle, which is completely inside this region. So it means I'll take this. What do you mean by I take this? Can anybody make that pink thing precise? How do I take that pink thing? Sorry, what was the last thing? Yes. Yes. We want to take the lower, right? Because the analogous thing, we want to basically take the rectangle which is contained in the region, right? So if you in that region, right? But then because it is not continuous, it may not have a minimum. So we'll take the infimum, okay? But we'll always assume that it's a bounded function, okay? Or at least what I'm saying is that on every interval, it is bounded. Okay, on every small interval, let you can assume, or let us just assume that it is bounded. Okay, yeah, for the moment, bounded. And so what we do is for this, the area of the contribution would be just epsilon because that is the thing, and the height is infimum of f. Maybe fx x. What should I do? I'll just call this pi. No, pk, kth part. Okay. This is the obvious thing. I'm just writing it. Just I don't know. It's not very needed to write it so clearly, but you write it. Now, in this case, we don't say a because we want to because it's a summation. So it's more than just an arbitrary count all the squares. It's a more it is that, but it is more than that. So we just put that linear thing in the picture. It's a lower sum, and I can say it's a lower sum with respect to epsilon. Just the same notation for the function f. Okay, so I'm not saying that region x equal to y equal to this and y equal to b and blah blah. You can understand when I say f. Okay. This region. This would be epsilon times. Yeah, just take summation of these things over k from 0 to whatever is needed. You can take. Okay, so this is just the smallest value. You don't have to stress too much on it. Okay, but we need to take the infimum. You cannot just take an arbitrary value and get away. Okay, you have to take the like if it is integrable, then no matter what value you take, whether you take infimum or supremum or any arbitrary value, you will get the same integral in the end when you let epsilon to 0 if it is integrable. Okay, just like if the function is continuous, then no matter what sequence you take, you get that limit. But if it is not, then you cannot take any sequence. So we have to carefully say this. Okay, so this is the meaning of under approximation. Okay, now if you would have taken a mesh of squares, it would not have been useful. It would not have been more useful, because if it was a mesh of squares, right, then you could have kind of added the squares along a column, and you would basically got this theory of rectangles only, more or less. So I mean, if one comes from there, which is usually not the case, one goes from here to abstracting there. But what we did, that is not needed in complete generality here. We can just take. Right, but that would not change the answer, right? Because finite sum at a time. Yeah, but then when there is an infinite sum, okay. But in this case, I suppose at each stage you have a finite sum, which you are adding. No, that should not affect. Yes, so it will be finite, right? So if it's finite, then it doesn't really matter, right? Yeah, that happens when the summation is infinite, right? Then whether you add row wise, column wise, then obviously it can become different. Okay. Yeah, cool. So then you take the upper sum similarly. Oh yes, yeah, because see, just like when we had the region, in this case, our S, what is our S? In this case, our S is this region. No, so the minimum may not actually exist, right? You may have to take the infimum because it's not a continuous function. Okay, and I'm not doing this just for like generality's sake, but because ideally you'll be looking at functions which are not continuous and have to decide whether they're integrable or not. Okay, so the minimum may not exist, but the infimum, then you have to take the infimum. And the infimum will exist because it is bounded. Okay. Yeah, is that okay? Okay, so that's why we're taking the infimum, okay? Because we want to first approximate the thing inside the blue region from inside. Then we want to approximate from outside. The inside of it corresponds to this only, and the infimum basically corresponds to taking the squares which are completely inside, right? Okay, so and then you take, similarly, you take the supremums and let's write it because see, supremums is what I'm saying. If you want to call it maximum, you can just call it maximum. It is not the same thing, but for understanding, you can just treat it like that. It's up to you. Just 1 minute, maybe. Yeah, okay. Right, this thing, right? And now, so what do we do now? What do we do next? Oh yeah, so that is certainly one way to put it. So you're saying that if there is a partition for which the lower sum becomes equal to the upper sum, then you can say that the integral exists, right? Hmm. Hmm. Yeah, like if you take like this. So you can say that, but that is not going to be good enough for most cases. So you see, if let's just stick with one partition for the time being. So this P, so first of all, notation, this P just represents the parts, and this is like, the partition. Maybe. So what I'm saying is, let's say you take this, let's not call it P1, just call it P. If you are considering a partition P, and you look at the upper sum, and then you look at the lower sum, okay? It may happen that the upper sum and lower sum are not equal, right? Ideally, the upper sum and lower sums, um, so you see, we can just write this, all of this just for a partition P, right? I just took the special partitions because they make the situation special and they're also actually good enough. But let's just take it like this if you're talking like that. See, this will always be true. Okay. Now, if for some partition it turns out that this is equal, then certainly we can say that the area exists. Then we should say, then we should define that to being that the area exists, right? Why? Because if let's say there is a partition, let's keep it for a moment for one partition. We can take union of partitions and so on, but let's say that for some partition P, they become equal. Okay. Well, what does this mean? It means now, or you can say for some epsilon or partition, you can see both terms. So if for some partition it becomes equal, now it means that if you increase, or sorry, if you decrease the value of epsilon, then this quantity is going to only increase, right? As epsilon goes down, right? And again, as epsilon goes down, this quantity is going to decrease, right? But then we also know that this is the lower sum is always less than the upper sum, right? So what does that mean? It means that it will remain equal. So if it becomes equal for some partition P, then it will remain equal for all partitions. I'm not proving this. I'm not proving it, but I'm just trying to see if it makes sense. Okay. Yes. So maybe I should say that. So let me say that first. So I think, yeah, before this, I should first, I'll just say a small lemma, maybe. Oh, 1 minute. Yeah. So let me say this first for this thing. So first thing is, look, if you take a partition P, then, and then Adish, I'll come to your question. If first take a partition P, you take a lower sum. So this makes sense, right? For any partition, this makes sense. I mean, right now we were just doing it like for this epsilon tagged thing, but you can do it for any partition. For any partition P, you take the lower sum. Then for that same partition, the upper sum is going to be bigger. This we all agree. This is in the definitions, bigger than equal to. But then there is more. There is this thing. If you take any partition, and this maybe I didn't say when we were doing the area thing, but never mind, that's not important. You know, we can do this. So now I've changed the partitions. Even then, so let's try to, someone should try to rigorously prove this maybe. So what does this mean? This means you take that partition, take the parts. For each part, you take the length of that part. It may not be epsilon. You take the length of that small part and you take the infimum in that part and you add it up. So the meaning is okay, right? Is the meaning, so first of all, is the meaning of this thing okay? What this means? Okay, I'll just draw that here. Meanwhile, you guys try to prove this. I'll just draw this. So then, so it's like A1. So the partition is A1, A2, like this. This is how, if you see like Rudin, that's a good book, or even Bartle and Shepard, Rudin, you will see these notations, right? This is, so this is a partition P1. P1 is, you could say like this, A1, A2, AN, or AN minus 1, this A, but anyways, that's bad. And then what does the summation mean? So then this thing, I was thinking something else suddenly, sorry. This thing means, what does this thing mean? So this thing just means, you can understand AI plus 1 minus AI, right? This is the length, and then you take the infimum. Yeah, you can understand what it means. this infimum in that region, X in this region, AI to AI plus 1, just in that piece. You take the infimum and you take the summation. Okay. But we want to show that for any two partitions, and these are actually not so, these are good properties that build it up, build the theory up. So that one has tools to in both directions to prove things are integrable and to also prove things are not integrable. Both ways you have the tools, because just understanding is not enough, right? This will be the last thing we do. So if you're taking two different partitions, then also the lower sum will be less than the upper sum. Hmm. Okay. Okay. But you don't know what P1 and P2 are. What is P2? I mean, how do you bring P2 here in the picture? Mm-hmm. Mm-hmm, mm-hmm. Right. So you think that if you take a finer partition, then the infimum becomes bigger. Is it something like that? Yeah. Yes. Yes, exactly. Yeah. So basically we need this notion of finer partitions, right? Otherwise, see, because P2 may not be finer than P1, right? So what do we mean by finer partition? Can anybody? Length, length is not good enough. You have to say basically that each part in, like, so we say that we will say that P and let's say Q is another partition. Then if each part of Q is inside some part of, yes, this is refined, right? That each part of P is inside a part of Q. Okay. So if this AI plus 1, so this AI and AI plus 1. Nested is not nested, it's contained. Nested is something, it is just contained. It's contained in a part, right? It will be contained in some Bj or BkBj to Bj plus 1, right? That's all. Nested is something different. Nested is when contained and then contained and then contained again, so on. Okay. So then we say that Q is finer than P. Okay, and that's even a partial order, but it's very interesting things can come up from there, but we don't need that much now. So we say Q is finer than P. Oh, this is the opposite, right? Yeah, we say that P is finer than Q. So I'll make this precise. P is finer than. So it's basically initially you start with a very coarse thing, right? Start with the coarsest thing, which is A to B, right? Then you add another thing, it becomes fine. Then you add, becomes more finer, right? The more intervals you add, kind of, it becomes finer and finer, right? And so what does this mean? So we say that P is finer than Q. It means that Q was there, you added some more lines, you subdivided Q further and you got P. But what does that mean? It means that every interval in P is contained in Q, some interval of Q. Is that right? One can also just say directly that if you write the parts of P and the parts of Q as a set like this, as we had written, then P will contain Q as a set. But that's just a partition only. That's what a partition is. Uh-huh. Mm-hmm. Mm-hmm. Yes, right. If you okay. Uh-huh. Mm-hmm. Yes. Yeah. So you're saying the second one. Okay. So the second one is finer. So can you say it again? 4 points. Uh-huh. So this is A, B, C, D, and then there is okay. So this is A. This is B, C, D. Oh yeah, C, D. Okay. Mm-hmm. That's an element. Okay. Uh-huh. Mm-hmm. Right. Right. And so then we say that S2 is finer than S1, but it's not in this case. Yeah, but how is this a cover? Because D does not cover CD. So S2 and S3 are both covers. So it's a set S, and S2 is a cover of S, kind of. So maybe we can just draw it here. So this is a cover. Okay, now you will say that another cover is a refinement of this if the the subsets which are used in the cover are contained in. So you take this red one and this red one and this red one. Then that red thing is a refinement, just in the natural sense. Okay. Yeah, this can be generalized to those actual covers and so on. And those are very important questions, but yeah, right. This is our case is like this, but I'll say this is in much more clear, concrete way is just as I've said. I'll just say it again. What we are doing is we are taking this AB, and let's say that what I'm drawing now is Q. So it's not a regular partition, okay, just Q. So this is Q. So these are the parts of Q you see. So that is one representation, but if it is like A1, or let's say Q1, Q2, because this concept is extremely useful in the problems that you do. So with this, so you could write Q using those parts, but Q is completely understood by the set itself. Maybe I'll write it like this: ordered set, Q1, Q2, Q3, Q4, and so on, right? And so on means just Q5, Q6. Now, what does it mean to say that another one is a refinement? Well, we have already written it. Refinement is finer. It means that these stones, you're going to break them further. You're going to refine them further, right? You're going to put further, you're going to break it further, okay? So what does that mean? Well, one definition is already here, that any part, so if P is a refinement, okay, it means you're going to break it further, which just means that for any part in P, okay, this AI plus 1, if this is in P, then that is actually contained inside something in Q. Okay, but then you see that just basically means that in P, that to get P, that means that to get P, we have just if we are keeping what is there in Q and we are further dividing it. So we are keeping what is there in Q. We cannot remove that, right? But we have to further divide. And that's what it means, right? You have to further divide it. You cannot eliminate the things that were there in Q, right? Because if you had an interval, one side was in Q, right? That interval would, yeah, so that you could take that interval, right? This interval in P, and then it is also in Q, right? But then it means that you see this end point had to be there in P, right? So if there is an end point which is there in Q, let's say this one here, and if I don't take that in P, if I remove it, then I'm in serious trouble, right? Because then I can take this thing and then this will be there in P but not be there in Q. So basically, simply put, I have to just subdivide further, okay? And that's, so that way what happens is this refinement thing can be written as set theoretic, that this P, if this P has this P1, P2, whatever, K parts, and basically this Q will be a subset of P in that sense. So it's a good thing. We're able to capture this refinement in a very good language, okay, of the subset containment. Refinements and such, right? No, then don't go into that. Yeah, don't go into the norm, because it will just maybe not lead to more insights at this point and just lead to more confusion. Maybe some notation. You can try to read. So Rudin is very good for this, from my experience. Rudin. Yeah, so Spivak is good. So others can also try from there just to get a hold of these things. Okay, yeah, Spivak also I remember a long time back when I read. It's also pretty good. Okay, but either ways, now you should try to prove this thing. Now it's very simple. Try to prove this. Basically, if you take this P1 and P2, and you have to take the common refinement of these two partitions, right? So you take the intervals that P1 has and you further add this, you get a P3, right? And the P3 will kind of, you take the L minus of P3 and then you take the L plus of P3, you can try to finish the problem, okay? And yeah. Yeah. So, okay, yeah. So you can say like that. And yeah. So then what we are going to do the next time I will not go more with the theory, because the theory is not, I didn't do what I wanted to do completely. But next time we will look at some problems. Like I'll just finish this little bit thing. You can maybe also read this, but I'll finish this for my sake. And then we will do some problems. We'll try to show something is integrable, not integrable, some strange functions. We'll do that. And also some problems are remaining from last time. I will do them next time. Uh, yes, I saw your mail. Yeah, actually, it was a very fantastic solution. And I missed certain things. That's why I didn't get the solution. I realized I'll talk about that next time. Not that it's already done, but it is correct. It is certainly correct. Yeah. But I want to just say a few things as about it, which uh-huh. Okay. Okay. From a different kind. Oh, that is good. Right. And also other problems are remaining from the test and so on. So I'll discuss them. And yeah. And then once we are done, then after that, we will prove some one or two theorems about integration. Yes. So certainly your solution is not correct. The answer is more than half to me, seems like, but I have not completed. It seems like the answer is infinite, unfortunately, seems like to me. Okay, but yeah, I'll try to see it. We'll try to see it next time. So next class we'll probably have on Saturday, and we will do these things. So we'll just do analysis for this week. I think this is good. Let's see, next week we'll do other things. Mm-hmm. 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 The lower sum will increase. Mm-hmm. No. Yeah, but you can. Mm, and there you do the reasoning. Right. So you take a third partition, which is a refinement. So you just you take the union of these two things. And there you see there the summation, the lower summation is going to increase. Yes. Yes. Right. And then you can see. So we have to go to this kind of, this is like the supremum in the poset of these two partitions. And there you have to do the reasoning. And this is a very common theme, whether you may have seen this in computer science also. You do the reasoning in the supremum or in the union set or something. Yeah, anyways, so this is the reason. But try to, maybe once you write it, you can see if there are more things to be said. Okay. So for others also, I just want to say, if you have any questions, you can ask. You can just take 5 minutes maybe and see if you want to ask any questions regarding what you have done today. Because you shouldn't be confused about anything if there is anything like that.